In our study in this chapter of the ideal gas law and kinetic theory, we next turn to the ideal gas law itself. It turns out, as you might anticipate, that there is a law that regulates the connection between the volume of a gas, the temperature at which it is, and the pressure which exists inside. If you just stop and think intuitively, if you think of a balloon, well, the outside is going to be at atmospheric pressure because it kind of balances the atmosphere. If I heat it up, it expands. So if with a constant pressure, if I add more heat, it expands. But if I were to confine it, like a steam engine, then in fact if I add more heat, the pressure goes up. If in fact the volume cannot go up. So there's a relationship between these three concepts, the pressure, the volume, and the temperature. And it turns out that the pressure, it's a linear relationship, that the pressure times the volume is the number of moles of the substance times a universal constant times the temperature. This is called the ideal gas law. Now in this, the pressure is of course given in our standard units of pascals in the SI system. The volume would be in cubic meters. This would be the number of moles. T would be the temperature in degrees Kelvin. And we have this universal gas constant here that's going to be written in joules. And it turns out a pascal times a cubic meter is a joule. And that's why we get a joule here. So that can kind of fool you. So you have to remember that this ideal gas constant, R, is 8.31. You can see the other decimal places, 4510 joules per mole per degree Kelvin. And that's an important constant. You don't have to remember that. That would be given at the top of the test normally. But you can see here that if I keep the temperature constant, if I double the pressure, I must halve the volume. If I double the volume, I must change the pressure by 1/2. If I change the temperature by a factor of 2 and leave the volume alone, the pressure is going to change by a factor of 2. And always remember, in all of these laws, this is degrees Kelvin. This would be cubic meters. This would be in pascals, or newtons per square meter. So we can change this just a little bit and write this equation in a different way by multiplying by Avogadro's number and dividing by it. And we do that by saying, okay, this is equal to N times, that's the number of moles, times, remember Avogadro's number, every mole has Avogadro's number of molecules, so this is going to be the total number of molecules. And we're going to take R and we're going to divide by Na. So that's the gas constant per molecule times T. And we're going to rewrite this, and this is now the number of molecules times a constant K, called the Boltzmann constant, times T. So we often rewrite this law as PV is equal to N times K times T. It's just another form, but instead of using the constant R, we use the constant K, where this is the Boltzmann constant. And this is the number of molecules. This is a little bit more fundamental equation in some senses of the word because it deals more with the atomic or the molecular level. And so sometimes if you're looking at chemistry, this might be the more dominant equation you'd use. If you're looking at statistical mechanics or statistics, this might be the equation you would more likely use. And as I've written here, this constant K, which is R divided by Na, is this constant K is about 1.38 e to the minus 23. That's in joules per degree Kelvin. So it's a very, very small number because you're dividing by Avogadro's number there. Now, this historical origin of this law is very interesting. Boyle first figured out that pressure times volume would be constant. If we held the temperature constant, then pressure times volume, Boyle said, temperature is constant, P1 V1 is equal to P2 V2. Same, let's say the same temperature. So if I have a gas, take the pressure times the volume, and I keep the temperature constant, but I change one of these, then obviously if I double the pressure, I must halve the volume, or double the volume, I must halve the pressure. So that was originally discovered by Boyle, and it makes sense. And you can see where it comes from. If this is a constant, this is constant, this is constant. So this would be constant for that gas. So P times V would be the same before and after any change. Later on, Charles observed that the volume divided by the temperature at one time is the same as the volume divided by the temperature at another time for the same pressure. And since we often deal with atmospheric pressure, then we can keep the pressure constant, and you can see if the pressure is constant, then we can divide the pressure through, divide the temperature through, and we'd have the ratio of volume to temperature, or its inverse, would be the same before and after a change. And it was Gay-Lussac who combined those two into one equation to give us what is called combination of the Boyle and the Charles laws by Gay-Lussac, a Frenchman who came up with the ideal gas law itself. Now, one is able to show by kinetic theory how where this actually comes from. You're able to show that the pressure times the volume of any gas is equal to 2/3 of the number of molecules times the average kinetic energy. But this is not a hard derivation. It just involves algebra and a little bit of work and looking at molecules as bouncing around within a box, and then you can actually look at the total random kinetic energy of these molecules. And now if we compare this equation with this equation here, we can see now that the temperature must be related to the average kinetic energy. In fact, the average kinetic energy can be proven to be 3/2 of K times T. And this, therefore, tells us what temperature really is. It is proportional to the average kinetic energy. How do we get that? This is an experimental law. It's not theoretical. It's experimental. We observe that in the laboratory for an ideal gas. However, we can derive this equation here theoretically. And since we know that this is true experimentally and this is true theoretically, then it follows that T, the temperature, is related to, by proportion, the kinetic energy. And is the average kinetic energy. Finally, in another equation, we're able to define the total internal energy. This is internal energy. And the internal energy is the number of molecules that you have times the average kinetic energy. I mean, if each one has a certain amount of kinetic energy and you have n of them, this gives you the total internal energy. Therefore, it follows from that, or this implies that the internal energy that's within something, which is kind of comparable to the heat, you might say, is going to be 3/2 of NKT, or equivalently 3/2 of nRT. So the internal energy is proportional to this temperature, because the temperature in this way, because the internal energy is dependent upon what the kinetic energy is, or the average kinetic energy. However, if you have twice as many molecules, if you have 2 bricks instead of 1, they still may have the same temperature, but I have twice the internal energy because I have twice the number of molecules. So you have to distinguish between the amount of heat, or the amount of internal energy, which increases with the substance at a given temperature. And this is the part that I would expect you to remember. If you remember this and you know what the kinetic energy is from our last equation, then you can easily substitute in the kinetic energy and find out what the total internal energy of a system is.